Okay. So getting a little preview into this is I wanted you to look at the numbers that we were working with. 32 is 8 times 4, right? And look at what happens when I put 30, like do log base 2 of 32. Now, guys, you don't get a calculator for this. So if you need to sit off to the side and say, okay, what are the powers of 2? 2 to the first, 2 squared, times 2 again, times 2 again, times 2 again. You can do that. We will not work with anything like super crazy. It's usually like 2 or 3 or 4 decently small numbers. But sometimes you have to write it out to be able to figure this out. So if I'm trying to find 2 raised to what, right? Isn't that what this question is? 2 raised to what gives me 32? There's 2 the first, second, third, fourth, fifth. So log base 2 of 32 is 5. Since I nicely have that list written out, we can kind of use that for the rest of these questions. Okay, well, what if I have it written like this? Log base 2 of 8, first, second, third, right, would be 3. Plus log base 2 of 4, 2 squared is 4, also 5. Well, 32 is 8 times 4. But notice the relationship is not that we multiplied those two answers together, right? We added those two answers together, and that's the log property we're going to start seeing today. That's what's eventually going to be called your product property. Very similarly, for divide, 16 is 32 divided by 2. 32 divided by 2. Look at how those are relationship, but that's not a divide symbol, right? 2 raised to the first, second, third, fourth is 16. Log base 2 of 32 is the same as we got up there, 5 minus log base 2 of 2. Log base 2 of 2 is 1. To get the same answer, I would subtract between the two of them. And so what you're seeing right there is your quotient property that we're going to see here in a few minutes in our notes. Similarly, down here is your power property that we're going to see. I don't have my 3's listed, so let's go 3. 3 squared is 9, times 3 again is 27, times 3 again is 81. And if I were then to think about, okay, 3 raised to what gives me 81? First, second, third, fourth. Okay, what if I put a 2 out front of log base 3 of 9? Log base 3 of 9 would be 3 squared, also 4. Well, what's the relationship? 81 is 9 squared, but see where that 2 ended up. Okay, what it can do is that's called their power property, which we're going to see in just a minute, ends up giving us the same answer and can allow us to work with some smaller numbers here as we head towards solving. Okay, today, again, like I said, we're learning the nuts and bolts. We're learning the tools to be able to eventually solve our exponential and logarithmic equations. And so this is our basics. This is what we're focusing on today, our product rule, our quotient rule, our power rule, which you just saw a preview to, expanding and condensing, which in previous life was called like factoring and foiling, putting things together, pulling things apart. Sometimes we needed a factor to do a problem. Sometimes we need to foil to do a problem. We need to know how to do both. At the very end today, we'll be introduced to this change of base property, which will allow us to evaluate a logarithm on any calculator, not just our fancy graphing calculators. So let's get introduced to those 3 rules officially. Product rule. The product rule says this: log base b, anything, of 2 things multiplied together, m times n. If they're multiplied together, I can rewrite those as log base b, whatever the original was, of the first term plus, and then we see that it repeated, log base b again of the second term. It's basically like they can each get their own log base b. The difference is it's now a plus between the 2 terms instead of a multiply. So seeing some basic examples of each of these rules in action. We have log base 6 of 7 times 11. I can rewrite that. I'm going to use an inappropriate math word here, distributing the log base 6, because that's not actually what's happening, but it's kind of what it looks like is happening. But understand the product rule translates then the symbol between them to a plus. So that log base 6 of the first term, this multiply tells me that my 2 logarithmic expressions are now going to be separated by a plus. log base 6 of 11. Now, can I simplify any of those in my head? 6 raised to something, give me 7. 6 raised to something, give me 11. No. When you guys have number ones at the end, make sure you do evaluate them if possible. If not, it's just going to stay like that. So here's an example of when we could continue to simplify. First of all, it says log of 100x. Two things I want to point out. If it just says log, what's the base? Base 10, right? And then notice there's no dot in there indicating multiplication, but when they're squished up next to each other like 100 and x, isn't that multiplication, right? So again, we can apply that product rule, which says I can do log of the first term plus log of the second term. And then this is what you need to look for. Again, if there's ever just numbers, continue to ask yourself, can that simplify? Okay, well here I'm thinking, can I raise 10 to something to give me 100? Yes, that can simplify. What does this equal? 2, right? That equals 2. And so you will need to simplify each of those if able. Well, I can't simplify the next one, so it'll just say log x. Questions? So when we can't simplify, remains log base 6 of 7 stayed as is because we can't evaluate that with our current tools. But this is one that we can do mentally, so we would simplify all of those. All right, next rule, the quotient rule. Looks almost the same. The difference is what's inside the original logarithm is a divide quotient. And the big change is then when we separate the two into their individual logarithms, we put a subtraction between the two. Log base b of m minus log base b of n. Again, we'll look at some very basic examples here to introduce our quotient rule. If we have something like log base 7 of the quotient 19 over x, and again, it kind of looks like distributing, but that's the wrong math word here, but they all are going to get a log base 7. So log base 7 of the numerator. And then because of the quotient, this will become a minus log base 7 of the denominator. Okay, just like we saw in the last one, you do need to make sure that you consider, can I simplify any further? So the next one we see is natural log of e to the 5th over 11. Remind me again, natural log is log base what? E. Okay, so initially I follow my quotient rule that says the natural log of the numerator minus, because of a quotient, the natural log of the denominator. And then we need to take a second and remember one of our log properties that we learned last week, and that is a reminder if you have something with the same base. Log base 2 of 2 to the 7th, if our bases match, isn't your answer always the other number, right? It is not appropriate to write an e as a base, but that's really what our base is, isn't it? It's log base e, which means our bases match. I would never write the e as a base, right? But because our bases match, this evaluates to the other number. This is just 5. Minus natural log of 11. That rule is tricky to see because you don't literally see the e sitting down there like you do when I write it as log base 2 of 2 to the 7th, right? So make sure that you always slow down when you see that you're plugging an e into something. Any questions? Last rule, power rule. And the power rule says if we have an exponent in our logarithm, that exponent gets to slide out front and become a what's called a multiplicative scalar or a constant multiplier, kind of some different math words that you would hear that described as. But it slides out front and it multiplies whatever we get from just doing log base b of m. A very basic example, again, would be able to rewrite something like log base 6 of 3 to the 9th. Anytime you have an exponent inside your logarithm, that I can take that exponent and slide it out front, and this would then become 9 times log base 6 of 3. Sometimes that just makes evaluating the logarithm easier. However, slow down. Can I raise 6 to anything to give me 3? No, that's kind of a tricky one. That's actually as simplified as that's going to get. But we would consider, can I simplify this? And you cannot. Okay. All right, there's your 3 basic rules. The rest of today is kind of seeing how those get incorporated into our process of expanding and condensing. We do need to look at the power rule just a little bit more closely, because sometimes it can look a little bit different, and that is when it can look like a radical. That's kind of like a hidden power rule, because a radical doesn't necessarily look like an exponent. So, but when you do see radicals, it is this power rule. And the first thing you're going to do is rewrite the radical as a fraction exponent. Okay. Once I do that, so this is a cube root. A cube root can be written as a 1/3. Now it looks just like we would have seen on the last page. We've got a fraction exponent, and all exponents can slide out front and become a constant multiplier, 1/3 times the natural log of x. But again, radicals will not initially look like that because they're radicals, but I can always rewrite a radical as a fraction exponent. Okay, and the last thing I want to make sure that you understand is if things are grouped together with parentheses and they are a plus or a minus, those will never, ever, 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 ever be broken apart. Okay, so that x plus 4 will stay a x plus 4 forever. I cannot break that. It does have a fraction, exponent, and so I can apply the power rule by sliding the 2 out front. But that x plus 4 will stay an x plus 4. It is not a product, so that log does not distribute, which again would be the incorrect mathematical way of describing that anyway. This is inside of our logarithm, okay? And it stays as a group. I know I've mentioned it before, but pluses and minuses are like the strongest bond in math, and you can never break apart a plus or a minus, okay? So it'll stay an x plus 4 forever. Any questions? Okay, so now, using those 3 properties, we are going to do essentially factoring and FOILing, pulling apart, putting together, okay? And depending on the situation, you may need to do one or the other when we get to the solving in the next couple days. So let's look at both. The first thing we're going to look at is what's called expanding, and that should be just like it sounds. We're going to pull it apart. We're going to have as many logarithms as possible so that everything has its own logarithmic expression. It says it may be necessary to use more than one property when you expand a logarithmic expression. You do not need to rewrite these because those are 3 properties we just went through, right? It's saying if you got a multiplication, you can pull them apart, put a plus between them. If you got a division, you can pull them apart and put a minus between them. If you got exponents, slide them out front. You will typically have to do more than one of those properties in the expanding and condensing process. So just some ways. Now this will kind of ebb and flow as you look at each problem because we might have to revisit certain steps or whatever. But some things to think about as you attack these. The first thing I always do when I am trying to expand my logarithmic equation expression is to take all exponents, take all radicals and rewrite them as exponents. Okay, so rewrite my radicals as fraction exponents. That's the first thing I'll always do. Now, these can be used more than once, whatever, but you're just going to go through and apply any of these that will be appropriate. Do we have any multiplication? Apply product rule. Do I have any dividing? Apply quotient rule. And then make sure that we also apply our power rule. How do I know I'm done? I know I'm done when I have no exponents left because I've slid all those out front as constant multipliers. And then I have a logarithm for each term. And again, the only thing that will not get broken apart is something that is combined with a plus or minus. If it's got a multiplier divide between it, all of those better each get their own logarithmic expression. All right, does anyone still want this page? Okay. So let's see this in action. And I know that for whatever reason, this one kind of printed weird on the page here, but it says use logarithmic properties to expand each expression as much as possible. So the very first thing that I said in my suggestions of how to attack this is that if we have any radicals, I would just rewrite this and change all radicals to fraction exponents. We do have a radical, and this, for whatever reason, printed kind of weird. Do you see that that's supposed to be a cube root of y? Okay. So the first thing I would do is I would address this whole cube root thing. And rewrite my radicals as fraction exponents. And I just go through and do all radicals. Okay. And now I start applying things like product and quotient rule. I typically save the power rule for the last, but you can kind of do them all at the same time as you start to learn how to do these quicker and quicker. But do you see how I have two terms in this one? I have an x and I have a y, and both of those should get a log base b, okay? Because they are multiplied together, it is going to be a plus between them. Log base b of x to the fourth, plus, because of our product between these, right? Log base b of y to the 1/3. And then finally, I would want to make sure that all exponents are my power rule slid out front to be our constant multipliers. So I've got two of those. I'm going to slide that 4 out front. I'm going to slide the 1/3 out front and get 4 log base b of x plus 1/3 log base b of y. Inside my logarithm, I have one single term with no exponent, an x here, one single term with no exponent, a y there. That's a good indication that I have fully expanded my expression. Again, kind of equivalent to the idea of factoring. And sometimes we had to factor to be able to solve. So sometimes we're going to have to pull this apart to be able to solve. All right, questions? Okay. Let's see, the concept we are about to talk on this page, and we will revisit it very in depth in the next like 3 slides after this, is this idea that is going to be super huge for you being successful with expanding and condensing. We have a quotient right now. Log base 5 of square root of x over 25y cubed. Again, my first thing I would do is rewrite any radical. So the first thing I'm addressing is my square root here. Okay. Quotient and product rule get confused when there are multiple terms in there and there's not literally just 2 things multiplied or 2 things divided. So if you can follow this rule, it's even better than thinking quotient and product rule is anything that comes from our numerator is always going to be a positive number. Anything that comes from our denominator is always going to be a negative or a minus. So when I am putting this, order does not matter. But if it came from our denominator, it's negative. If it came from our numerator, it is positive. And what confuses people is this is a product, and so they want it to be plus between those two, but they both come from my denominator. Both should have negatives in front of them. Okay, so following that, we would have a log base 5. Do you see how I have 3 things up there? I should have a log base 5 for x, for 25, and for y. Numbers are a term as well. Okay, so I'm going to separate all of those. Log base 5 of the x to the 1/2, positive because it came from my numerator, minus log base 5 of 25, negative because it came from my denominator, minus log base 5 of y cubed, minus because it came from my denominator. All things numerator are positive, all things denominator are negative, and final step is to slide all exponents out front. And there's one little thing that might trick you in here. When I do that, there's actually one more thing I could clean up. Does anyone see what that is? I can do this, can't I? I can do this. Log base 5 of 25. What is 5 raised to what gives me 25? 2. So I can also evaluate sometimes. There is my fully expanded form. Not always, but sometimes I can evaluate, and if I can, I should. All right, how are we doing? Yeah? Okay, let's put it back together. Condense. So this would be the same idea as like foiling. We're gonna put them all together, okay? So write the sum or difference of two or more logarithmic expressions as a single logarithm, and that's your key, is that we get a single logarithm. Notice all of these are backwards. They were separated by a plus. I can put them back together as a single logarithm with a multiply. It's the same three properties, working your way backwards, taking them from separated back to a single logarithm. Okay, here's our steps and goals. The very first step I will always do is start by moving all scalar multiples, which means those numbers sitting in front, back to being an exponent. Same thing as we did. After I've done that, now start applying my power product and quotient rules. Again, all positive things came from our numerator, all negative things came from our denominator, putting it back together to be like one fraction or one expression. And the last thing I will ensure to make sure that I am done is that we have rewritten all fraction exponents as radicals, and you should only have one logarithm when you are done. Log, base, whatever, and only one of them. Okay, questions? Anyone still need this page? Okay, let's see some examples of condensing. I'm going to start with some very basic ones. A very basic example would be something like log of 25 plus log of 4. There are no scalar multiples to slide back as exponents, so then I start thinking through my product quotient power rules. We have a addition, which tells me as we put these back together to be one log, that it would be translating into multiplying those 25 times 4. Okay. As always, when it is all numbers, we do need to evaluate if we can simplify further. Well, 25 times 4 is 100. Can I simplify log of 100? Yeah, 10 raised to what gives me 100? 2. So sometimes we can simplify all the way down and not have a logarithm left at all. Emma? Yes. Okay, sometimes we can't. So here we have some variables in there, probably means we cannot simplify any further than just putting them back together. I get that there is a plus sign in this one, but it is not separating logarithmic expressions, right? The sign that is splitting our logarithmic expressions is a minus. And so that tells me that this is an example of a quotient rule. As I put these back together, I should be dividing one logarithm. Inside my logarithm is a fraction. The 7x plus 6 would have been from my numerator. The minus x, so that x would have come from my denominator. Now, just a notational thing, that logarithm is sitting out front of your fraction, or the fraction is inside your logarithm. The logarithm is not in the numerator, it's not in the denominator, it's kind of sitting like right equal with like the bar of the fraction, okay? Some people like try to put it inside the fraction, like up in the top or something. It's sitting outside. This is all inside your fraction, okay? Okay, let's get into some a little more complex here, where we have to do multiple things. 2 natural log of x plus 1/3 natural log of x plus 5. So if I go back to the steps that we had on the first page, the very first thing that I would do is always just look for those constant multipliers and slide them back to being exponents. So I have a 2 here, I would slide that to an exponent, 1/3 here, slide that to an exponent. That 1/3 does apply to the group. So as I go to put that back together, that 1/3 will be of this x plus 5. Because of the addition between them, that says when I put it back together, I would have multiplied those two. Right, you don't need the dot there, but just for our notes purposes here. And then the last thing I do before I say that I'm done is make sure that I take all fraction exponents and rewrite them as radicals. So that one again, to finish this one up, I would have a cube root of x plus 5. Rewrite that fraction exponent as a radical. Okay. Still good? Try this one on your own. First thing you should have done is slid that x back to, so the 2 back to an exponent. Then the fact that it is a minus between those, as I write it as one logarithmic expression, that tells me that this following the minus should have come from my denominator. If there's no anything separated by plus or minus, you don't need that big parentheses. It's not a requirement. I tend to write it anyway just to remind myself of what is all inside that logarithm, but not a requirement. Okay, let's get into our more complex ones here. This is where I would stress the same thing I talked about earlier. Remember that as we are looking at, it doesn't matter which direction you're headed. Positive terms are numerator terms. Negative terms are denominator terms. Order does not matter. So as I look at this, eventually down the road, seeing a positive sign here means that whatever this term was came from my numerator. Seeing a negative sign here means whatever that term that follows it comes from my denominator. And a negative here means that whatever follows that came from my denominator. Okay, order does not matter. Follow the signs. Okay, still start by sliding all of those constant multipliers out front back to exponents. And now I start just separating positives to the top, negatives to the bottom, and make it into one fraction with a log base b out front. All positive terms, numerator. So my x to the 1/4 was positive. It came from my numerator. The 5 squared had a negative out front. It came from my denominator. The y to the 10th had a negative out front. It came from my denominator. Okay. The last thing we need to look for in this, there's two things we need to fix, and we haven't talked about one of those. One thing we have talked about is rewriting fraction exponents. Right, that'd be a 4th root of x. Does anyone see what else we could fix? 5 squared, right? I can fix this. Always, if you have a number raised to an exponent, always fix that. That one is also needs to be done before we consider ourselves done with this problem. And that would have been a 5 squared is 25. Okay, so those are kind of the last two little things we needed to finish on that problem. Okay, so I've sat these two side by side so that you can see very obviously that order does not matter, and positives and negatives just tell us where to put things. It's our last example of condensing. And so notice it goes positive 1/2 log base 3 of x minus 2 log base 3 of 4 plus 5 log base 3 of y. And again, follow that same rule. Positive things come from your numerator, negative things come from your denominator. I'm going to start by sliding all of those exponents back, all of the multipliers back to exponents. Okay, when I took those, notice I left the sign. It was a minus here. It's still a minus between those, right? So I'm leaving the sign there because, again, the sign is just telling me where to put that term. And so as I then go ahead and put those all into one log base 3, again, I'm going to have a fraction because we have some positives, some negatives. The x to the 1/3 goes numerator because it was positive term. The 4 squared goes denominator because it was a negative term, but now the y to the 5th is a plus again, so that's going to go back to my numerator with a multiply between them. So finish this one up, clean up the cube root and the 4 squared, log base 3 of cube root of x times y to the 5th, and you can put the y to the 5th in front of that if you want to, over 16. Why is it what? Because I wasn't paying attention to what the original problem was. Watch this. Fixed it. I don't know why I started writing it as a 1/3 instead of a 1/2. But now it matches. Any questions? All right. The last thing we need to talk about is what's called your change of base. So this is where our calculators come into play. Your change of base says this. Any logarithm can be evaluated on any calculator, scientific. Your nicer, newer graphing calculators have an option to type in any log base anything, but not all scientific calculators do, okay? So there's this thing called change of base formula. And the change of base formula says this: I can rewrite any logarithm to have any base I want it to by doing this. Log base, fill in whatever I want, of what was originally inside, divided by log base, same thing that I just picked, of what the original base was. So why would I change it? Well, what if this was like a 2 and my calculator doesn't do that? All scientific calculators can do a common log, which is log base 10, and can do a natural log, which is log base e, natural log, right, ln? Like I said, your nicer graphing calculators, I'll show you where that is. But let's look at this change of base. Your book does ask you to show change of base in 2 different ways, using common log and natural log. So let's see one side by side here. When they ask us to evaluate using common log, that means log base 10, okay? So what I do is I take the expression they gave me, log base 7 of 2506, and I'm gonna write a quotient, log base 10, common log, of the original inside of the big number, divided by log base 10 of the original base. Now, just a little calculator note, grab your calculators. When you go to type this in, you need to locate your log button. If you're looking at a graphing calculator, mine is on the left-hand side, 4th button up. It will probably be in a different location, obviously, if you're looking at a scientific calculator, but let's locate our log button. When I hit that, it will give me a parentheses. Before I continue, I will need to close the parentheses, then hit divide by, and type in log 7. When you do that, you should get 4.02. If you are not, you're going to talk to me about what you're typing in. Approximately 4.02. You can also type it in as a fraction if you have that option on your graphing calculators. Okay, I want to show you side by side because we can do this with the common log, base 10. What if I chose a different base, natural log? I'm going to rewrite this as ln, or base e. Notice that I gave you the exact same problem. We should get 4.02 again. So I would do it again, natural log of the original insides, or the big number, 2506, divided by the natural log of the original base. Natural log is typically right next to your log button. Mine is right below it. It says ln, 3rd button up on the left-hand side. Make sure you close that parentheses again, but again, when you type this in, you should get 4.02. 4.02. Now, if you happen to be doing this problem with your graphing calculator and you have the newer version of graphing calculator, will you guys hit your math option? Left-hand side, like third button down-ish. Mine is option A, so like way down at the bottom of the list, it says log base. My newer operating systems on the graphing calculators will allow you to just type in log base 7 of 22506 and tell you that it is also 4.02. So just so you know that that's an option here. Now, if I had only given you a scientific calculator, you have no choice to evaluate this, but to use your change of base, because scientific calculators don't have this fancy thing that graphing calculators are showing us. Questions? All right, guys, you have a My Math Lab assignment tonight. Make sure you go find the correct one. It is number 47 for section 3.3. You may.